Hey everyone, so in today's video we're going to be talking about a very important theorem in calculus that is called the mean value theorem. It's actually kind of a two-part theorem. There's one part as it applies to derivatives and there's one part as it applies to integrals. They end up actually being this different wording of the same theorem, but we'll go over the integral one later in the second semester when we talk about integration. But for right now we'll just talk about this one. And basically this is a theorem that essentially just says over some interval, which we will call between the points A and B, if we have a function that is continuous and both differentiable over that interval, then there's going to be at least some x value, we'll call that x equals c, which satisfies this particular equation. Now it's important that the bounds on c are given between A and B, so C cannot be equal to A or it cannot be equal to B. It's got to be something in between them. But what this theorem is basically saying, if you look down here, is that when we look at this equation, well, you guys have seen this equation before. That's the equation for average rate of change over the interval A to B. And this is just the derivative, or the instantaneous rate of change of the function f at a specific point C. So what this theorem basically states is this. Let's say we were looking at a car that accelerated uniformly from rest. So we'll have velocity on the y-axis and time on the x. Let's say it accelerated from 0 to 60 miles per hour in some time. You know, the time is t, it doesn't matter, okay? Well, on average, if we were going to determine our average velocity between that point, despite the fact that our final velocity is 60, our initial was 0, and all the other velocities hit points in between there. So in this case, our average velocity, we'll call that the average, that would actually be equal to 30 miles per hour, okay? So what the mean value theorem states is that there is some value c, in this graph the c would represent a time, where our instantaneous rate of change is equal to our average rate of change. So if we're going to accelerate from 0 to 60 miles per hour, there has to be some point in which our current velocity was 30 miles per hour. So that's all that the mean value theorem is pretty much stating. So let's look at how we solve this in a couple problems. So this first problem says that, let's say we're given the function f of x equals x squared. So we want to find the values of c which satisfy the mean value theorem over this interval -1 to 3. So if we evaluate this, well, this will be the average rate of change, f of b minus f of a over b minus a. Now this is just evaluating f prime of c. Now keep in mind that if f of x is x squared, f prime of x is going to be 2x. So therefore f prime of c is 2c. That is why we have this equation right here on the right is equal to this equation right here on the left. If we solve that, this equation turns to 2. We get 2 equals 2c, or c is equal to 1. Okay? So if we're going to kind of visualize what this problem would look like, we can come to this Desmos file, and here you see we have our function f of x equals x squared. We have our a and b values right here. Right here we define our average rate of change between those values, and then here this f sub p of x, that's just our derivative of the current function. So look at this equation right here, all right, this one that I'm highlighting. Average rate of change minus f prime of c equals 0. Well, this thing is just another way of saying, remember the average rate of change is f of b minus f of a over b minus a. We want to find where that is equal to f prime of c. Well, all this equation says is it just takes the f prime of c and subtracts it from both sides. So we get f of b minus f of a over b minus a minus f prime of c is equal to 0. And this represents, this value c represents the solution to that equation. Okay? So if we clear this ink right here and we look at this function, what do we see? Well, we see the red line is the function x squared. The blue line right here is representing the slope of this secant line connecting our two endpoints at a comma f of a and b comma f of b. What does that slope mean? Well, that slope again is the average rate of change. And now, what is this dotted black line? Well, the dotted black line is the slope of the tangent line. And what point is it at? It's at that point x equals 1. So the slope of this line would be f prime of 1. And what do you notice about the slope of the dotted blue line and the dotted black line? Aren't they the same? Well, this is a visual representation of what the mean value theorem gives us. Okay, the mean value theorem just tells us there exists some point, as long as between our interval a to b, that our function is continuous and differentiable, there is some point where the average rate of change will equal the instantaneous rate of change. And graphically, it looks like that's the case we have right here. The slope of the tangent line to the curve is the same as the slope of the secant line connecting our two endpoints. So therefore, this again is a visual representation of average rate of change equal to instantaneous rate of change. All right, so let's have you guys try a problem on your own. So do me a favor real quick, because I forgot to put a square on here. Close your eyes and don't open them until I tell you to. If you guys actually do this, I will give you a cookie in class or something like that. So close your eyes. Let me go to the next slide and put a little square over this thing. Oops. All right, are you keeping them closed? You better, or you are getting absolutely no cookie in class tomorrow. All right. Oh my gosh, Notebook, you're killing me with drawing these squares. Okay, obviously I'm having a problem with the Notebook software. When does that ever happen in class? Okay. All right, cool. Open your eyes and now look at this problem. All right, so we have given the function f of x is x cubed minus x squared. Find the values of c which satisfy the conditions of the mean value theorem on this particular interval. So go ahead, give that a shot, pause the video. All right, so if you were able to try to work this out, the first thing you should have done is to, was to evaluate our average rate of change and our instantaneous rate of change. So our average rate of change is going to be over the interval. Again, this right here refers to f of b. Remember, f is this function x cubed minus x squared. This refers to f of a. And then we have b right here and a right there. Now this right here is the derivative. So if f of x was x cubed minus x squared, f prime of x would be 3x squared minus 2x, and f prime of c would be this thing right here. I'm just plugging in c's for x, okay? So is that all good? So if you didn't get to this part or you didn't get this right, again, pause the video and try it again. Let me clear the ink right here. Okay, so give it a shot. All right, pause the video. All right, if you've tried it again, and we scroll down to the next line, we see, something like this. So this is just solving for both sides. If we solve for that average rate of change right here, we're just going to end up getting the value of 5, and then we still just have 3c minus 2c. So I bring that 5 over to the other side, and hey, check it out, we got a quadratic equation. How do you solve a quadratic equation? All right, let's get you guys some practice. You could use the quadratic formula right here, but you can actually factor this thing. So give it a second, try to factor this thing. It would be good practice with factoring. Pause the video. All right, if you gave that factoring a shot, let's look down at what we end up getting, and we get something like this. It factors into 3c minus 5 times c plus 1. This has the two solutions, which make this 0 of c is negative 1 and c is 5/3. Now, you may have gotten to this point and said, oh, cool, I found two values of c that work. It doesn't turn out that that's true. Let's go back up to the original problem. Look at the wording of the original problem and tell me if both of those c values work. What's the one problem with one of them? Well, the one problem is coming from this c is coming from the value of C is equal to -1. And the reason why that gives us a problem, come on, yep, sorry about that. Oh, where is that stupid line? There we go. Okay. So the reason why C equals -1 gives us a problem is because, go back to the criteria for the mean value theorem, it says that C has to be between our values of A and values of B. It cannot be equal to A or B. So C equals -1 is actually not a solution of this. If we had found another solution to this equation that would have said like C is 5, that also would have been invalid because it's not in this particular interval, okay? So in this case, the only one that actually works by the mean value theorem would be 5/3. And if we go back to our Desmos file to help visualize this, let's come up here and let's switch our function to x cubed minus x squared. And we're going to have to change our tangent line here to include that value of 5/3 everywhere. Let's do that one more. All right, so now that we got that, look at this again. Again, the dotted blue line represents the secant line connecting our two endpoints from this point down here of A comma f of A, and then the point up here of B comma f of B. So remember, that blue line, the slope of that blue line is our average rate of change. The slope of the black line will be f prime of our value C, which in this case is f prime of that value we found 5/3. And doesn't it look like the slopes of those two lines are equal? Again, we've got a situation where our average rate of change is equal to our instantaneous rate of change at that particular point. So that's the mean value theorem. If you got questions about it, come in class tomorrow ready to ask them.